we're trying to answer the question why charged particles can exert a force over a distance. And we know that if a force acts over a distance, then we consider it a non-contact force. And anytime you have something like a non-contact force, we have a way that we think about it. So can you think of any other non-contact forces, by the way?
Gravitational.
There is the gravitational, and there is also magnetic, which we haven't covered yet, but we will cover in soon.
Mm-hmm.
So you've got different types of non-contact forces, including the one we're studying right now, electrostatic, gravitational, as well as magnetic. And our idea of how non-contact forces work, for example, how can this positive charge repel this positive charge? How can this force work? The idea is step one, you've got a positive charge. Step two, this positive charge creates an electric field. So it creates some sort of field that I'm going to draw kind of like this for the moment. So this is like an electric field. And once you've got an electric field, then the next thing after that is this electric field interacts with this positive charge, so particle 2. So particle 2 interacts with the field and, kind of feels the force. So anytime we talk about a non-contact force, the way we're describing it now is you've got a particle that's charged. It can create an electric field that I've just drawn like this for the moment. And this electric field will just kind of go in all directions.
Mm-hmm.
And then some other particle, in this case, a positive charge particle here, will then, because of the field, then it feel a force. So we're not saying particle 1, directly repels particle 2, although in shorthand we say that. But if we want to explain it a bit more, we say particle 1 creates a field, and it's because of the field that the particle 2 then experiences a force.
Okay.
And that concept, although we don't really do gravitational fields until, year 12, or like next term, basically, and magnetic fields later this term, the same concepts apply. So if you understand electric fields well, then you'll get a head start on these ones, all right?
Yeah.
So your electric field then, what does it mean? Well, actually, it's pretty easy. What it really means is it's a vector field, so it's made up of vectors, and it basically shows the direction of the force that a positive charge will experience at that point. So let's start easy. Let's say we've got a positive charge here, and we want to draw the field around it. So if I've got a positive charge up here, at this blue dot here, which way would it go? If I've got a positive charge here, what would happen to it?
Move away from them.
So which direction is that?
Wait, are you talking about north or?
Okay, we'll just go up here.
Yeah.
What about here? What would happen to it?
Further up.
So we'll just go up. What about here?
Still up, but not as far.
Well, we don't care about the far right now. We're just saying it's the direction, right?
Oh, okay.
So let's say we're here. Which way would it go?
Right.
If we're here,
Right. Oh, that's down.
if we're here.
Left.
And then once we've got all those, we just join them up.
That's it.
And simplistically, that's my electric field for a positive charge. Because as I said, the field just simply shows the direction of the force that a positive charge will experience at that point. So anywhere on this line, it's just going to go up. If I put a positive charge anywhere on this line, it's just going to go up. Anywhere here, it's just going to go right. Anywhere here, it's going to go down. Anywhere here, it's going to go left. All right. And we could do something similar with a negative charge. And if I have a negative charge, what's going to happen if I put a positive charge here?
Positive.
Yep.
Like pull towards the negative charge.
Right. So you can, I think, you know, having done the positive, it's probably pretty clear that the negative will do the same thing, basically, except this time you'll go directly to it, right?
Mm-hmm.
So one kind of shortcut that people like remembering, I suppose, and it's not wrong generally, but basically, you know, electric fields go from positive to negative. And that's really because of the definition of what an electric field is. The electric field is something that shows the direction of the force on a positive charge. And a positive charge will obviously go away from a positive charge because we said it repels, and it will go towards a negative charge because it is attractive, and that's why it will do that.
Mm-hmm.
Now, that's really simple, but we could now sort of make it a bit harder. So let's consider the situation where we now have a positive charge and a negative charge together. Now, let's imagine that you are a positive charge as per the definition, and you're here. What's going to happen to you and why?
Move towards negative charge.
Well, why is that, to be clear? How do you know it's going to go to the right?
Because like in an electric field, the positive moves towards the negative.
But more specifically, how do you know that's the direction of the force? What forces are you experiencing?
Non-contact.
What's giving you the force? How many forces are you experiencing?
Electric field.
So what I'm basically saying is that this positive charge will repel you to the right.
Yeah.
And this negative charge will attract you to the right.
Yeah.
Since both of them are pulling you to the, or pushing or pulling you to the right, then it's very clear that you're going to the right.
Yeah.
But, and of course, anywhere in the middle here is also towards the right. But the point I'm trying to make here is that there are two forces and you need to think about both of them. Yes?
Okay.
So what if you're here?
Moves toward the negative. Still left.
Why is it moving left?
Because the further the distance, the weaker the force.
Yes. So really, we're saying that let's use yellow. So the yellow, you know, you've got a attractive force from the, you know, from the negative, and so basically this is like the, you know, the yellow one, and this is like the red one. and the red one is repelling it, but not as strongly. So overall, it is still heading left, as you were saying.
Mhm.
And that's because of Coulomb's law. And so because of the increase in distance, it is going left. So you can see that anywhere over here, it's going to be attracted and repelled, but the repulsion will always be weaker than the attraction. So all over here, it's going to be left as well. What about here?
Moves to left.
Right? For the same reason, you're going to get repelled by this quite strongly. You're going to be attracted, but relatively weakly. So the two will fight, and the repulsion will win in this case, and then you're going to move left. So anywhere here is pretty easy, right?
Mm-hmm.
Okay, what about here?
Oh. Moves. I reckon stays.
I won't stay.
I think move to the right.
So how do you get that? Well, it's basically a vector addition. So you can see that this is going to attract it in this direction with some magnitude.
Mm-hmm.
So it's basically going to pull it that way. But this positive charge was going to repel it. So there's a vector this way, but you need to add it on to vectors. So it's just your vector addition that we've done many, many weeks ago.
Mm-hmm.
Which then means that the net result is just going to go to the right.
Mm-hmm.
All right, what about here then? Let's do it here. Let's think of somewhere here.
Then it's that way and that way.
Well, which one's stronger?
On that one, that
The
one,
attraction?
that one.
The attraction is stronger?
No. The repulsion is stronger.
Well, then you've got the wrong length written, right?
Yeah.
So the repulsion is stronger because it's closer. So if we kind of think of it as your components, we've got a relatively weak attraction, relatively weak, going that way,
Mm-hmm.
and then a relatively strong repulsion, which is like that, which then means that it's kind of going more up, right? And similarly, if we kind of work out the point here, you'll see that it's relatively strong attraction, but relatively weak repulsion. So you're kind of being forced a bit to the right. But basically what that means then, and if you keep going doing this, you'll basically get this result. That's basically the result of a positive negative charge electric field. Now you see all the electric field lines do have starting from positive and going to negative. Now the only straight lines are along this axis. Everywhere else it's kind of curved because of the vector addition aspect. But that's basically the idea, right?
Mm-hmm.
Now, question. Will the field lines ever not start from a positive? Like, you know, or do they have to all go all the way to the positive? Can they kind of stop and not go all the way here?
Sorry, can I say it again?
So your field lines, they have to start from your positive, okay? Because there's a force that it can experience all the way in between, right?
Uh-huh.
And they must go all the way to the negative because otherwise, you know, your force, you know, if it's here, it'll still attract to the negative. It won't just stop here, you know? It'll go all the way to the negative.
Mm-hmm.
Now, these are field lines. Can these field lines cross each other?
No.
No, because remember, a field line is meant to show you the direction of the force. Now, if you've got a field line crossing each other, then you're telling me that at this point here, the particle goes in two directions. That doesn't make sense.
Mm-hmm.
The particle can experience more than one force, but then you need to add them up and work out what the sum of those forces are.
Mm-hmm.
So the field lines, the final result, can never cross. Okay? So remember, field lines do not cross. Because it doesn't make any sense. All right, what if I had a positive charge and a positive charge? What would that field line look like? So if I've got it over here, which way would it go?
Left.
Yep. Over here, kind of go right.
Right.
Yeah. All right. What if I've got something here? What would it look like?
Like that.
So what we're saying is basically that you'd end up with, if you're here, for example. So let's start easy, right? If you're kind of here, then that basically means that you're going to be fairly strongly repelled and moderately repelled, meaning that you're kind of going more up, right? And if you're here, you kind of be going more right. So basically, you would kind of get this sort of situation happening. Okay, so that's basically the idea, okay, for your field lines. Now, looking at the field lines, the next thing I want to ask you is, do you think that if you're a positive charge and if you're close to the positive charge, do you get the same force as when you're far away?
No.
No, you don't. So when you're closer, you get a stronger or weaker force?
Weaker.
When you're stronger, you feel
Stronger.
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 You get a stronger force.
Yeah.
Now, a stronger force means the field is stronger or weaker, do you think?
Field stronger than.
Right. So the field has to be stronger close to the positive charge, and I'll add a few more lines in. And it must be weaker as you go out further, right?
Mm-hmm.
Now, right now, we've only focused on the direction, and the key thing is the direction, generally. But now I want you to think about the strength of the field. So we know it's stronger closer to the positive charge, and it's weaker further away. Can you see a difference between the area closer to the positive charge and further away? Can you tell a difference in terms of the field? Can you see a difference?
The amount of arrows.
It's not so much the amount of arrows, but you're kind of similar on the right track. It's the number of lines in a given area.
Mm-hmm.
It's how close the lines are together.
Oh, okay.
So remember, your field, and this applies to all your fields, not just electric field. So your fields, remember, represent the direction of the force experienced by a positive charge. All right. And the positive charge part is for electrostatic field, which is the one we're studying now. And the density of the field lines in other words, how close they are together, represent the strength of the field. So we can clearly see that in the case of this, for example, close to the charge is a stronger field, further away from the charges, the field is weaker. For electric fields, and remember, because of that, field lines cannot cross. Now, for electric fields, we say that the field lines go from positive to negative because of this idea that they represent the direction of the force of the positive charge.
Mm-hmm.
So the next question we're going to be thinking about is this. We know that particles do not have the same electric field strength depending on distance. How do we create an electric field that is uniform in strength?
Draw two parallel lines.